For Mohrs circle, to determine anything about a circle, you need the center of the circle and the radius of the circle. And we know that the center, which is sigma c comma 0, is sigma x plus sigma y divided by 2 comma 0. So that would be sigma x here is minus 80 and sigma y is 50. So all that divided by 2. This will come out to be minus 15 comma 0. So nothing new, we've done this before. The radius of the circle is sigma x minus sigma y divided by 2 the whole square plus tau x y square. And so this comes out to be see, minus 80 minus 50 divided by 2 square plus here the stress 25 is actually negative because the way I've drawn it, it is if you look at this and if you look at this is going back way back where I talked about the stress element here. Right here, you can see that the way I've shown the stress, shear stress is counterclockwise on the sigma x direction. That was considered positive. So here the stress would be negative. Not that it really matters here, because eventually it'll get squared. Okay, so this comes out to be 69.6. Okay, so center is known, the radius is known. Let's go ahead and plot this draw the Mohrs circle and show these coordinates. I need to be mindful of this. It's minus 15 and then the radius. So let's do that. Okay, I'm just going to draw a circle, remembering the debacle I had last time where it was all messed up. So circle. And then when I'm showing the axis, I think that this is approximately the center. It should be the center is at minus 15 comma 0. So let me go ahead and draw the, say this is the origin. That would be sigma. And then the tau axis would be something like this. So that is tau. And then the radius is 69.6. Actually, I should not have drawn it here. Okay, so that's the Mohrs circle. Now, coming back to the problem, we need to compute the stress as 30 degrees. But before that, remember always 30 degrees is with respect to this face. So we need to identify where this face, or it could also be this face. Let's just do this face. This face is on the Mohrs circle. In order to do that, we need to plot minus 80 and 25 on the plot. So I need to plot face A, which is minus 80, and then that the other one would be minus 25. And the reason why I put, sorry, my bad, it should be plus 25. The convention is that clockwise is positive. So I need to, so this would be positive 25. If you want to do that for face B, the stress here is 50 MPa, tensile, so it's positive. And then on this face, we have the shear stress, which is acting in the counterclockwise direction, and that is That's negative. Let me just check my convention. I think I written it down earlier. So clockwise will be positive, counterclockwise will be negative. Clockwise positive. Let me write that down. CW, CCW. So CW is positive, CCW is negative. Okay, so on face A, we have clockwise, that's positive. And then on face B, we have counterclockwise. We'll turn the element this way. So it's negative. So negative 80 plus 25 and plus 50 minus 25. Okay, so I need to plot this. So minus 80, I'm just going to guess it's somewhere here. Minus 80, and then I need to go up. This is, so let's just call this the point A. And then the other one is 50. Let's assume that 50 is, should be a similar distance, 50. And then minus 25. That's P. And I need to join them, and that is basically the diameter. So it should pass through the center of the circle. Okay, so now I have the face A, face B, and when I say 30 degrees, it's basically 30 degrees clockwise about face A. Now, if you go back to the Mohrs circle, you'll see this thing, which is when you rotate by theta s, you rotate the plane stress element by theta s, you actually rotate by 2 theta s on the Mohrs circle. Same for theta p. If you rotate by theta p on the uh, you rotate by theta p on the stress element, you always go 2 theta. So what we're looking here is we're trying to rotate by 30 degrees for the plane stress element. So we are interested in rotating 60 degrees clockwise direction for the Mohrs circle. So we go back to the Mohrs circle and rotate this by 60 degrees. So 60 degrees clockwise. I'm going to make a guess that 60 degrees is somewhere here. Okay. And if you want the stress on the other face, you just extend this line. So let's call that A prime. This is B prime. And this is also 60 degrees. Again, 60 degrees clockwise about face B. Okay, now what I'm interested in doing here is I'm interested in computing the stress sigma and tau for A prime and B prime. So I need to write down the stress here and then the stress there. And that was pretty much what the question asks me to do. So for that, what I can do is I can actually use some trig to figure that out. What I had found earlier, I think, in the past for this problem was that, so this is a calculation you need to do again, is where is the, so I did find something about the angle which this face A makes with the horizontal or the principal axis. So we know what theta p is. It was, I think, 10.5. So if 10.5 is theta p, then 2 theta p is 21 degrees. So I know that angle. It'll just help us to do the trigonometry faster. So this angle is 21 degrees. This was computed in example 1. Okay, so if that is 60 degrees, and this is 21 degrees, so it's 81. So this should be 9 degrees because this whole thing is at 90 degrees. Okay, so with that, I think that should give me enough information to compute the coordinates of A. I'm just going to redraw this part of the circle separately so I can do some trig. Let's call this the origin. This is A prime. This is A. This point is minus 15, 0. So I need the distance of A prime on the x-axis and along the y-axis. So this is R. This angle is, well, you could use that angle or you could use, might be just easier to use. This is 9 degrees. This is shown there. So we're interested in this distance. Since this is R, this distance here should be R sine of 9 degrees. And then this distance should be R cosine of 9 degrees. So it's easy to see that from the fact that O is minus 15, we can see that A prime, the coordinates of A prime would be minus 15. This is the x coordinate, minus 15 minus this distance. So that distance is R sine theta or R sine 9 degrees. And then the y distance, which is this distance, is simply R cosine 9 degrees, but it's upward. So simply R cosine 9 degrees. So this comes out to be R is 69.6. So if you do the math, it comes out to be minus 25.89 and 68.76. That's A. And then we also need the coordinate of B, which can be obtained if you do the same thing with point B. Just extend the line down, use the fact that it's 9 degrees, and then you'll see that B is. So I would like you to figure that out and just verify the math. It comes out to be minus 4.1 and minus 68.76, sorry. Okay. So I would like you to check this yourself using trig. So that's part one, which is figuring out the stresses at A prime and B prime. The next step is to draw the plane stress element in the rotated configuration. So that's fairly straightforward. All we do is say that this is part, I think it's A and is it A and B? 1 and 2. Okay. This was 1, and then this is going to be 2. So the original element is drawn like this. We need to rotate this by 30 degrees in the clockwise direction. So we need to do that here, where this is 30 degrees clockwise. But more importantly, we need to show the stress. So here we have, so this is A, which will be, my bad, that's counterclockwise. So that was not right. So what you're doing here is I'm rotating this, the black dotted line by 30 degrees in this direction. So this face will now, you know what, I'll make it, this might be better to understand. So if you have this line, then this line, which you see, the green dashed line, will now be here. Okay, and then the face B dashed line would go right there. And this angle is 30 degrees. So what happened here was the stress of sigma A was negative. This is sigma A. It now moved over here. This is sigma A prime. And I think sigma A prime was computed to be minus 25.89. This was minus 80. For B, we have so let's draw stress P, sigma B, that was 50 MPa. And so that would rotate this way. And this would be sigma B prime. And sigma B prime was computed to be, it's compressive 4.1, is that? 4.1. And the last one we need to draw is the shear stress. So that shear stress, which was originally this way, is now going to be in this fashion, like this. And then we are told that the calculation showed us that that stress is 68.76. So it's 68.76 for A prime. So remember that convention is clockwise. Clockwise is positive. So at face A, we'll have show a clockwise stress of 68.76. So at A, this is the new A. The stress is clockwise. This is correct. The direction I've shown is correct. And then if you look at B, it's minus 68.76. It's B prime. So if you go back here and look at face B, it is counterclockwise. And so counterclockwise negative sign. So this is correct. So this is also 68.76. So it's very important that you not only draw the element in the correct configuration, but you also show the right direction for the new stress. Shear stress is normal stress. So this is the new shear stress. Okay, now this is how you would do it with using Mohrs circle. Now, if you don't want to use Mohrs circle, you can actually use the formula. So another way without using the Mohrs circle. Okay, so this is based on the formulas I wrote down. One of the formula I wrote down, I abbreviated as 1 as sigma is sigma x plus sigma y divided by 2. plus sigma x minus sigma y divided by 2 cosine of 2 theta plus tau xy sine 2 theta. And then I wrote another formula. This is the transform formula for shear stress. It is minus sigma x minus sigma y divided, minus outside the bracket, sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cosine 2 theta. Okay. So here, if you want to compute the stresses on face A or A prime, what you do is you put theta is minus 30 degrees, that's clockwise. You put sigma is minus 80, sorry, sigma x is minus 80 MPa because that was the original normal stress. And then sigma y is 50 MPa with a positive sign. And then tau xy, the way it is shown, if you go back to the problem, you can see this is 25 MPa, but the way it is shown on face A is that it is clockwise, and clockwise is, oh my bad, sorry, you should go by, you should actually go by this figure, because this figure was used, this was the, okay, this is hung. Okay, here it is. So this was the original figure I drew some time back to derive the equations. So this figure shows you the assumed direction for tau xy, and this was used in order to compute a formula for sigma and tau. This is the formula I wrote down earlier. So in this convention, tau xy is positive if it is counterclockwise for face A. Okay, so this is a different convention from that used for Mohrs circles. So don't get confused. If you're using the formula, you should stick with this figure. Okay, this figure. And this figure has positive tau xy is counterclockwise. So in this case, going by the figure, we have (25 MPa), but 25 MPa is shown in a different direction, or the opposite direction as what we started off. And so this has to be negative for tau xy. So I need to put minus 25 MPa. So yeah, I just put a note saying I see the first page. So it's the first page of this particular notes. Okay, so now if you see this formula and this formula, everything in this is known except for sigma and tau. So if you put in the values, you get sigma A, this is at face A, sigma A prime would be minus 25.85, and tau would be minus 68.79. Okay, what this means, now if you look at this answer, so, and you compare it with the answer I had some time back, minus 25.89 plus 68.7. So you saw that the answer is, the x value is fine, but the y value or the tau value is actually flipped in sign, because again, I'll remind you that Mohrs circle uses a different convention for what is positive for shear stress. This is not the same as what we used for our convention, which for the formula is this convention, and for the Mohrs circle is a different convention. So the sign is actually makes sense, because when you draw this element in the rotated configuration, you will see that it will be not this way. That way is positive by that figure on the first page. It'll be this way. And then the stress, the compressive, is on face A, and tau would be 68 point. Okay, so this is the stress on face A. we still need to compute the stress on phase P. In order to do that, everything in this formula, the sigma x, sigma y, tau xy remains the same. The only thing we need to figure out is what is theta for phase B. Okay, so phase B actually is at 90 degrees to phase A. Always true, right? So if phase A is this, phase B is here, there's 90 degrees. So all I need to do is I just need to substitute, add 90 degrees to theta, and we have 60 degrees. And that's basically what goes for phase B. So here I'll write for phase B or B prime, we can B prime is at 90 degrees to phase A prime. So the new theta here is 90 minus 30, which is 60 degrees. Sigma x is the same as before. Sigma y is 50, same as before. Tau xy is the same as before. It's 6 minus 25. And then we use formula 1 and 2, which I wrote down on the previous page, and solve for the stress on phase B. The stress on phase B comes out to be minus 4.1 MPa, and the shear stress for this particular phase is positive 68.79, which, by the way, if you check this sign, you'll see that the sign is negative for the Mohrs circle, again, because of the difference in convention. So if you finally want to redraw this part 2, part 1 was figuring out the stresses, then it will be the same figure. Take the figure, the stress element, rotate it counterclockwise. This is at 30 degrees clockwise. And then you just draw the stresses. Sigma B prime, which is minus 4.1, sigma A prime, which is 25.85. The shear stress, which is this direction, is 68.79. This is the answer to part 2. Then this and this answer is solution to part 1.